Good evening, seniors, and welcome back. Today in AP Calc, we're going to be talking about particle motion. Now, I'm calling this particle motion, but really it's a broader topic, and you could use this stuff that we're going to be talking about today to talk about or to illustrate the motion of a ball when thrown, or a cannonball, or a bullet if you fire a bullet out of a gun. Any sort of projectile motion this would describe. Okay, and so as we start working through these problems, we're really going to focus on the relationship between distance, velocity, and acceleration. And this is a really cool relationship. And if you think about it, it makes a lot of sense. And there's tons and tons of problems on the AP Calc test and just and applications in the real world in general that involve the relationship between distance, which is x, the distance of an object. X is a function of time. Velocity, which is lowercase v as a function of time, and acceleration. Which is lowercase a as a function of time. It's also, sometimes x is the height, it's labeled as the lowercase h. Sometimes acceleration is g because it's just assumed to be gravity. Most projectiles they're under the force of gravity on the earth. So sometimes those change, but mostly it's v or x, v, and a. Now, if you already know this relationship, that's fantastic. Hopefully, I'm going to give you a little bit more information. If you don't know this relationship, pay close attention. This is really important. Now, the idea with distance or with position, x of t, is if I have the position of some object over time, and I take the derivative of it. So if I find dx dt, this is going to be equal to the velocity. Okay, or I could say another way of writing this is x prime of t is equal to the velocity of t. Right? So if I have some function, perhaps it's the path of a ball. If you throw a ball up in the air, as the path of a ball sort of travels, you have, if you're to plot this out on xy coordinate plane, instead of xy, it would be time versus distance or height. Say it's height x. As the ball is thrown up in the air, over time, it's going to start coming back down to Earth. Now, if you take the derivative of this, this will give you the velocity. Okay, the velocity function, which is really important, right? You need to know when the ball, for example, has zero velocity, right? And so if you think about if I throw a ball up in the air and then it comes back down, right? There's going to be a point where it's going to have zero velocity, and that's going to be at the very peak. So if I take the derivative of this function, right? And remember, the derivative is related to the slope of the tangent line. So the tangent line in this case goes like that. It has a slope of 0. That means the velocity is going to be 0. So the derivative of this function equal to 0. That's the velocity. So it's going to have 0 velocity at the arc, right? So if I throw a ball up, it's going to stall out just right at the top of the arc, and then it's going to come back down. It's going to accelerate on the way back down, or it's going to go faster on the way back down. Now, the relationship between velocity and acceleration is if I had v of t, if I take the derivative of the velocity, dv dt, with respect to t, this is going to give me the acceleration with respect to time. Now, most problems you're going to encounter are going to have a constant acceleration because most of the problems that you see on Earth are like a ball being thrown up in the air, and the Earth, fortunate enough, has constant acceleration. However, if you're talking about things like a car, right, if you hit the gas on a car, right, so here's gas brake, if you just hammer down on the gas, you're going to accelerate, right, so you're getting pulled back into the seat for a while, but then eventually the acceleration slows down, right? That force that you're feeling that's pushing you back into the seat lets up, right? So the acceleration in that case is not going to be constant, so it's going to be a function of time. And so once again, similar to the velocity, or similar to the distance, the derivative of the velocity is going to be equal to the acceleration, or v prime of t is equal to a of t. Now, once I know this, right, so if I say v prime of t or x prime of t is equal to v of t, and I've got this between v prime of t and at, I can find the relationship between x and a, right? So I've got x and v and a, and I can look at the relationship here. So x prime of t is equal to v of t, and I've got this equation right here. So basically the short end of it is if I take x prime of t, excuse me, and I take the derivative of it, this is going to be equal to, all I did here was v of t right here. I took this x of t instead of a v of t right here, I plug the x of t into here. Right? So d of x of t is going to be equal to a of t. Or the derivative of x prime of t, I can also write that as the double derivative. X double prime of t is equal to a of t. Cool. Now we're getting someplace. Okay, so I've got these three relationships that are related with the derivatives. I'm just going to, I can underline them here, but I'm just going to put them over here as well, and box them, just because they're so important. I want you guys to know them. Okay, so I can say v of t is equal to x prime of t, the derivative of the position. I can also say the acceleration, a of t, is equal to the derivative of the velocity. Or I can also say the acceleration is going to be equal to the double derivative of the position. Now this relationship goes one way with derivatives. It goes the opposite way with antiderivatives, or integrals. Right? So if I look at this function right here, this is the relationship between these three with derivatives. Now let me look at what happens when I start here, x prime of t. Say I'm not given x of t, right? And I'm not given a function for x of t, but I am given a function for v of t. So what can I do here? Well, if I take the derivative, or if I take the integral of both sides of this, so if I integrate x prime of t dt, and I integrate v of t dt, right? So I'm not angering any of the algebra gods by doing this, right? Or the calculus gods in this case. I'm basically just taking the integral of both sides. Well, the antiderivative of the derivative of this primed here is just going to be exactly x of t. And this is going to be equal to, I can't simplify this equation enough or anymore, so I can say the integral or the antiderivative of v of t dt. Cool. So now instead of if I'm given an x of t, I can calculate v of t, and this one if I'm given a velocity, a function of the velocity, I can calculate what the position is. This is great. So I'm working backwards, looking at that reciprocal, that opposite relationship between derivatives and antiderivatives, or derivatives and indefinite integrals. So now I can continue this on. I can look at the relationship between v prime of t. So I can do the same thing. I can say v prime of t is equal to the acceleration, a of t. So if I integrate both sides, integrate v prime of t dt, integrate a of t dt. So this simplifies down to, I basically just get v of t is equal to the integral of the acceleration function dt. Cool. Now we're getting close. Now the last one right here, I'm going to go ahead and save this one. I'm going to shelve this one for a little bit because you basically need to take the double integral, right? So just how I have v of t is equal to this, I can continue on, and instead of v of t, remember v of t is x prime of t, so just rewriting this, I can say x prime of t is going to be equal to the integral of a of t dt. And once again, just like I did up here, in order to get rid of this integral, or in order to get rid of this prime, I integrate both sides. So if I integrate x prime of t dt, then I'm going to integrate again this acceleration function. So this looks like this. So I've got a double integral here. I know this is probably the first time you guys are seeing this. Don't freak out. It's super cool. It's not that hard. Just like double derivatives weren't that tough, double integral is not that tough. Double integral of a of t, and then you would say d squared of t. So that's just telling you need to take the derivative, or the antiderivative, twice. Now this you can simplify into the integral of the derivative, the antiderivative of the derivative is just going to be the position. X of t is going to be equal to integral a of t times d squared t. Cool. Now this is my other relationship here. So in this one we were going with the derivatives. And in this box over here, we're going to go with the integrals. So we're going to say x of t is going to be equal to v of t dot dt. We've got v of t. I'm just rewriting these functions we just derived. V of t is going to be equal to the integral of a of t dt. And x of t is also equal to the double integral of a of t dt. Now, enough deriving for now, right? All you need to know is we figured this one out with derivatives. This is a relationship between these three things with derivatives. This is a relationship between these three things with integration. So let's jump into an example. When do we use this? Okay. So suppose I have a ball. Here's an example for you. I have a ball, and I'm throwing it upwards. So a ball is thrown up. And just like anything, if I have a ball and I'm throwing it up, I'm going to have an initial height, right? I'm not going to throw it all the way down from the ground. It's going to have some initial height, and it's going to have some initial velocity. Okay? So my initial height is 80 feet. My initial velocity is 64 feet per second. Okay, so the height, this is distance. The velocity, this is a velocity. So it's distance over time, feet per second. Now, the question that I'm asked is, what is the position? First question, A. What is the position x of t over time? Now, this might seem like an impossible question to answer at this point, but we have enough information to do it. Okay, the one piece of information that you guys need to know, you need to have memorized, is what the acceleration due to gravity on Earth is, right? Mars is going to have different gravity, Moon is going to have different gravity. Those are different problems. They will give you that. But the acceleration due to gravity on Earth is 32 feet per second. And not just feet per second, but feet per second squared, right? So velocity is distance over time, acceleration is distance over time squared. And I'm putting a negative here because the acceleration due to gravity goes downwards, right? So it's not like you're accelerating away from the Earth. You're always accelerating towards the Earth. Now this matters because you need to know which direction you're going in, right? So if you're as long as you're going down towards the Earth, it's going to be a negative 32 feet per second. So in order to find the function, right? So I know that x of t, right? This is what I'm looking for. I'm looking for that integration relationship. And based off of the page that I just had, I know that x of t is going to be equal to the double integral of a of t dt, or d squared t. Now this is kind of freaking me out right now, so I don't want to deal with this. We'll eventually understand how this is working, but what I'm going to find first I'm going to find what the velocity is, the velocity equation. V of t is going to be equal to the integral of a of t dt. This is one of those other ones that we just derived. Now I'm looking for the indefinite integral. I'm not exactly sure what the limits are going to be in this case, but I'm just looking for this indefinite integral. Now, all I know is a of t, okay, and I know these initial conditions here. So with this, I can actually solve this. So v of t, let me just rewrite this equation right here. So integral, now a of t is negative 32. That's it. It's just a constant. It's a very simple function. Negative 32 dt. That's it. You guys can do this integral. Nothing to it. So when you integrate a constant, right, you go x to the n, or in this case it'd be t to the n plus 1 over n plus 1. Or when you integrate a constant, it's just going to be, this is going to be equal to negative 32 t. And then of course, because it's an indefinite integral, there's going to be some constant here. Now this is going to be my velocity function. So velocity as a function of time is going to be equal to negative 32 t plus c. Now before I get too far, I need to start plugging in these initial conditions. So the initial velocity, 64 feet per second. Okay, that means at time is equal to 0, or v sub 0, then the velocity is 64. Okay, so I know that when time is equal to 0, v is equal to 64. So this is an initial condition. In this case, I'm going to go ahead and plug that in here. So when time is equal to 0, I can say v of 0, right? So everywhere I see a t, I'm going to replace it with a 0, negative 32 times 0 plus c. And this is going to be equal to 64. Well, this sort of becomes a little bit simple and almost unexciting. Negative 32 times 0 is just going to be 0. And so I'm just left with c is going to be equal to 64. So this initial condition, just like when we were dealing with initial conditions with integrals, it allows me to solve for c. So now I can write the complete function of v of t with my one initial condition. So I can say v of t is equal to negative 32t plus, I just solve for what my c is, plus 64. Great. I'm like halfway. I'm like 3/4 of the way done with this problem. So now I need to realize, okay, I've got this relationship, right? Or I've got this function for v of t, and the next relationship that I'm going to try to solve for is x of t, or the next function I'm going to try to solve for. And I'm going to use the relationship that x of t is the integral of v of t dt. Now all I need to do is replace v of t here, so I'm going to do that. So integral, I just solve for v of t here. So I've got negative 32t plus 64 dt. Once again, I've got a simple integral here, right? It's just a power rule integral, nothing to it. So I can basically just say, okay, x of t is going to be equal to, and when I do this integration, I end up with negative 32, and it's going to be t to the n plus 1 or 1 plus 1 over n plus 1. So I get t to the 2 divided by 2 plus, and then same thing, I'm integrating a constant here. This is just going to be 64, that's a 4, t. And then, of course, I've got another c that's tagging along, right? Now, don't get these confused, and just keep it straight. I should actually probably have said this is going to be c1, and this is going to be c2. They're going to be very different constants. Now, let me rewrite this a little bit simpler. All right, so this negative 32 over 2, I'm just going to write as negative 16t squared plus 64t plus c2. Now, I've got to do the same thing with this c2, okay? Now the other initial condition that I was given was the initial height is 80 feet. This means that x of 0, so same thing, x at time t, so when t is equal to 0, that's what the initial means, time is equal to 0, the height, or x, is going to be equal to 80 feet. So t is equal to 0, x is going to be equal to 80. So I'm going to use this information, plug it into the equation to figure out what c2 is. Okay, so I'm going to say x of 0 is going to be equal to negative 16 times 0 squared plus 64 times 0 plus c2 is going to be equal to 80. And once again, this almost becomes unexciting, but 0 plus 0, that goes 0, that goes 0. c2, I just end up with c2 is going to be equal to 80. So now I can rewrite the entire function. X of t is going to be equal to negative 16t squared plus 64t plus 80. And this is going to be my entire function. Now, if I wanted to plot this out, it would look something like this. So this axis is going to be time, this axis is going to be x of t. And what happens is you're starting off at 80 feet, okay? And remember, you're just throwing the ball straight upward. So it's going to have some upward velocity, some upward trajectory. So it's going to go straight up in the air. I know it kind of looks like it's actually traveling distance, but this ball is actually going straight up in the air. It's just changing in time. So it's going to max out somewhere around 150, and then it's going to come back down to the ground, all the way down to 0. Okay, so somewhere around t is equal to 2, it maxes out somewhere around 150, and we can figure out exactly what that is once we know what this equation is. So we started with very little bit of information. We figured out what the exact position of this is. Okay, we're going to pick up from here tomorrow, talking more about particle motion.